Hi, in this session we will be discussing about the single phase transformers. We will try to understand the basic principle of the transformer, the construction, equation for EMF and the different types of transformers. Okay, what is meant by transformer? Transformer is a static device which transfers an electric energy from one circuit to another without change in frequency. So we will define transformer as the device which can convert the electric, which can transfer the electric energy from one circuit to another without changing frequency. Why it is necessary to use the transformer? Means what are the different applications of transformer? The primary application of the transformer is transmit and distribute the electric power over a long distance, and hence they permit the generation process to avail in a remote place. So generally the voltage will be generated around 11 kilovolts, and then later this voltage level will be stepped up with the help of a transformer nearly around 132 kilovolts, or could be 220 kilovolts or 400 kilovolts for transmission lines. This conversion helps the transmission of huge electric power at lower cost. Since we know that the high voltage line carries the low current, and hence the cost of line and the power loss are tremendously reduced. Once it is being transmitted, that is at the distribution point, we will make use of the step down transformer to bring the voltage levels down to nearly 400 volts or 220 volts, and which can be used for the domestic purpose, industrial purpose and for the office usage. Another application is, since there are no moving parts in the transformer, it hardly needs less maintenance or sometimes no maintenance, and also needs less supervision. Small transformers can be used in communication circuits, in radio and the TV turn circuits, telephone circuits, instrumentation, and also in the control systems. We will make use of the audio transformers for coupling the amplifier stages, that is to match as matching devices for microphones and the record players. Therefore, the audio transformer helps to carry on the two-way conversation over a single pair of wires. Now let us try to understand the working principle of the transformer. So transformer basically works on the principle of mutual inductance between two coils. Let us say it in detail. Okay, so before this, this is how the transformer construction looks like. The vertical portions, we call them as limbs, this one, and this is the core part, the iron core part. Top and the bottom parts, we call them as yoke. And it has primary turns and then primary windings and the secondary windings. Primary winding, generally they will be having n1 number of turns, and secondary windings, so let us call n2 number of turns. Why we call the windings as primary and secondary means, since the winding is given to the supply and it is being named as primary, and here this windings are called as a primary windings because it is being given to the supply, and the winding for which load is connected, we call them as secondary windings. Okay, now basically the two principles are involved in the operation of transformer. Firstly, the electric current produces the magnetic field, we call it as electromagnetism, and Secondly, the moment between magnetic field and a coil will induces the EMF across ends of the coil, and we call it as electromagnetic induction. A changing current in primary circuit will create a changing magnetic field, and this change in magnetic field induces the EMF or the voltage in the secondary circuit. Hence, the energy is transferred from one circuit to the other. That is, in order to understand the principle of mutual induction, whenever we provide the supply here, there will be current flowing through the primary coil, and it produces the magnetic flux in the core part, which we have indicated with this dashed dotted lines. This is the flux. Whenever there is a change in magnetic flux, the EMF will be, or the voltage will be produced across the secondary coils, and we can connect the load, and we can measure the amount of current which flows through the secondary or the load terminals. In brief, whenever there is a change in current, magnetic flux lines will change, and this induces the EMF. This process we call it as mutual inductance between the two coils. Here the primary and the secondary coils, they are not physically connected, but they will come in contact whenever the flux gets produced in the core part. Okay. This figure B, it indicates the symbolic representation of the transformer. This is the primary winding having N1 number of turns, secondary winding N2 number of turns, current flowing through the primary coil, and the EMF at primary, EMF at secondary, current flowing through the secondary coil. So by having the different ratios N1 to N2, the power at lower and at higher voltages can be obtained. When the number of turns at secondary is greater than number of turns at primary, that is when N2 is greater than N1, we call such transformers as a step-up transformer, and when N2 is less than N1, that is secondary number of turns is less than number of turns of primary, we call such transformers as step-down transformer. Okay. So we also classify the transformers into different types that we will be discussing later. Okay. Now let us see the equation for EMF for the transformer. So whenever we know that whenever the sinusoidal varying voltage, that is input voltage V1, is applied to primary of the transformer, this voltage will produces the magnetic flux in the core, and we can represent the magnetic flux as phi, which is phi m sin omega t, where phi m represents the maximum or peak value of the flux, and f is frequency of the sinusoidal variation of the flux. So as per the law of electromagnetic induction, the EMF induced can be represented as E is equal to minus n times d phi by dt. Sorry, this has to be d phi by dt d phi by dt. This should not be there. Minus n into d phi by dt, that is change in flux with respect to the time period, and the EMF induced will be depending on number of turns of the windings. So we know that the flux produced is nothing but phi m sin omega t. So let us substitute that over here and differentiate with respect to the time period. We will get minus omega n phi maximum cos omega t. So here why we have indicated the negative sign means always there will be an opposition to the source. And this minus cos omega t can also be represented as sine of omega t minus pi by 2. And the EMF will be maximum when this sinusoidal term is equals to 1. And the maximum value of EMF we can represent it as E max is equal to omega n into phi max. Therefore, let us substitute this E max in the equation of EMF in this above equation. So we can rewrite it as E is equal to E maximum, and therefore which is nothing but an average value. Here since for the AC parameters we have to consider the RMS value. So let us find the RMS value here. RMS value is nothing but E maximum divided by root 2. Therefore, let us replace omega with 2 pi f, and on simplifying we will get the RMS value of the EMF induced as 4.44 Fn into phi maximum. So I'll just repeat one more time. Whenever we give an input voltage to the primary of the transformer, this will produces the magnetic flux in the core, and we will represent the magnetic flux phi as phi m sin omega t. So according to the electromagnetic induction, we can write the EMF induced as minus n d phi by dt, which is equals to, now substituting the value of phi as phi m sin omega t and differentiating, we will obtain it as minus omega n phi m into cos omega t. So we can replace minus cos omega t as sin omega t minus phi by 2. So the peak value of the EMF can be represented as omega n phi maximum. But here we have to obtain the RMS value. Therefore, RMS value is E maximum divided by root 2. So which is nothing but omega n phi maximum divided by root 2, and hence this is equals to 4.44 Fn into phi maximum. Now, so let us see the construction of the transformer. So as I said just now, it has the two main parts, the magnetic core and then windings. The magnetic core is either rectangular or square in shape, and the core is divided into two parts, yoke and then limb. It is generally made up of silicon steel. Core is generally made up of silicon steel, which can have the high permeability and low hysteresis coefficient. So the vertical portion, these portions we call them as limb, and top and bottom portions we call them as yoke. Okay. Now, and coming to the winding, basically we will call them as primary winding and the secondary winding, P and S winding. So primary winding will be having N1 number of turns, secondary winding will be having N2 number of turns. And they will be having lamination kind of structures. Mainly these lamination structures will be used in order to reduce the eddy current losses. And these laminations are insulated from each other by a thin coating of suitable varnish. And the thickness of lamination will generally ranges from 0.35 mm for a frequency of 25 Hz to 0.5 mm for a frequency of 50 Hz. So the lamination strips are assembled where the joints are staggered to avoid the narrow gaps all through the cross section of the core. Okay. Next, let us see the different types of transformers. Based on the construction of the core, we will classify the transformers into two types. One is core type transformer and another is shell type transformer. So this is what the core type transformer diagram looks like. Let us first consider the core type transformer. So in this, the windings will be surrounded by the considerable part of the core, so which we can observe from this figure A. Here the windings are surrounded by the core, and both the windings, they are divided into two parts, two half parts, which are placed on each side by side. So this is generally done in order to reduce the leakage of the magnetic flux. And look into the second diagram. So here this the low voltage and the high voltage windings arrangement. Adjacent to the core, the low voltage winding is being placed, and next to the low voltage, the high voltage windings will be placed. Okay, next is shell type transformer. So here in shell type transformer, it has three limbs. This is one limb, center limb, and then another limb. There are three limbs here, and the windings are being wounded in the middle center limb. So in the second diagram, we can see the how low voltage and then high voltage windings are being placed. So here the low voltage and high voltage windings are placed just one on the other. They are sandwiched on one or the other. So one more difference between core and shell type transformer is, so we can observe here, there is only one path for the magnetic flux. There is only one dotted lines we can observe, which is a flux here. But in shell type transformer, we can clearly observe that the magnetic flux gets divided into two paths here. So there are two paths for the magnetic flux. Then one more difference is the shell type transformer is more economical for the low voltages, and the core type transformer is used for the high voltage applications. That's all about this session. Thank you.